Hi, I'm John Kerr. I'm with Andritz out of Glens Falls, New York, and my company makes screening and cleaning equipment for the pulp and paper industry. And I'm here today to talk to you about the screening of recovered fibers. A typical flow sheet for a recovered fiber plant for packaging grade includes many unit operations, some of which are shown here. The idea here is to show you that screens are used throughout the system in a variety of places and for different purposes. We have a pulping loop, which typically is to primarily prepare the pulp, that is, to make it in a pumpable slurry and remove some of the gross contaminants. The next stage of unit operation is, of course, screening, and we'll do coarse screening with holes in that particular position. Might be followed with fine screening or fractionation, as it shows in this flow sheet. Fractionation is intended to separate long fibers from short fibers and could be done with either holes or slots, but in this instance probably done with slots. Then the long fiber fraction would be further screened with slots in order to remove the sticky debris. Slotted screening is the #1 technology that's used for removing macro stickies, or stickies that can cause problems on the paper machine and defects on the sheet. Other places we'll find screens would be in the head box loop, but we're not going to address those in particular. But it's interesting to note that head box screens have evolved from being always holes to sometimes now using slots. And so this technology is equally applicable in the head box loop at low consistency. Screening plants in a de-inking system, on the other hand, also follow pulpers, would be coarse as using holes, fine using slots, then followed by, in this case, flotation and cleaning and other unit operations, and then at some point would usually see fine screens again, that is slotted screens prior to dispersion for final removal of sticky debris or other contaminants. Of course, the screening loops aren't just standalone screens by themselves. They are always multi-stage affairs where we'll arrange the screens such that the fiber is recovered in the subsequent stages and the debris is removed ultimately from the tail end of the system. In this graphic, you'll see a three-stage coarse screening system. There's a primary coarse screen whose function is to remove the flakes and the debris, concentrate that debris so that the deflaking screen, which is in the secondary position, has some material to work with. And in that position, we'll want to add some additional horsepower into the screen. We'll want to have a different type of screen so that we can do some fiber recovery by treating the flakes in particular. Those accepts from the deflaking screen will then go to a secondary coarse screen, which is much like the configuration of the primary coarse screen, and its efficiency is going to be approximately equal so that the pulp produced in the accept stream can be fed forward. Doing so makes the entire system smaller, much more capital competitive and floor space competitive. The deflaking screen will commingle its rejects with the plastic debris, and so it needs to be put across a tailing screen for ultimate fiber recovery, but that fiber quality is going to be commensurately lower in terms of its contaminant level. The contaminant level is going to be much higher, the quality is going to be lower than the primary or the secondary coarse screen accepts, so it will be recycled back into the process. The tailing screen is also responsible for disposing of the collected debris in the coarse screening loop. The fine screens, however, are organized somewhat differently. They also have a 3-stage, maybe 4 stages, depends on the capacity of the system. But the primary fine screen, of course, will be responsible for the majority of the production and, of course, all the quality. The secondary fine screen will be of a similar design as the primary fine screen. Therefore, we can expect the quality of the accepts to be quite similar. So it's not unusual at all to see a secondary fine screen accepts being fed forward as well in order to make up production and make the whole system size smaller. The tertiary fine screen is again of similar construction, but because of the increased contaminant levels that come from the feed of the primary to the feed of the secondary to finally the feed of the tertiary screen, the contaminant levels are going up and up and up with each successive stage, so the accepts of the tertiary screen are not expected to be of sufficient quality to be fed forward. Again, that tertiary screen or that final stage screen is responsible for the ultimate disposal of the collected debris. This is a graphic of a typical centrifugal screen which is used in a lot of coarse screening applications. Now the artist concept here has ghosted in the feed nozzle, so look carefully and you can see that there's a feed nozzle here which accepts the pulp comes in, rotates around, and then eventually makes its way but in the annulus between the drum rotor and the screen basket here. Okay? I'll show you in the next graphic. This is what we're talking about. The feedstock comes in. There's typically kind of a rock trap arrangement or some sort of barrier protection to keep the nuts and bolts and the dog hairs out of there. And the stock will spill over and go between the annulus between the rotor and the screen plate. The screen plate is stationary. The rotor, of course, is driven and acts to agitate the pulp in order to mix it up to equal out the consistencies from the top to the bottom of the screen. And basically improve the screen operation. Accepts go through the screen plate and are removed. The rejects are then collected in the reject chamber and removed separately. We might add dilution water in the bottom because of what's known as a thickening factor. The thickening factor is a mathematical calculation between the rejects consistency and the feed consistency. It's the ratio of those two consistencies. And is a good rule of thumb measure about the performance of the screen itself. If you have an excessively high thickening factor, that indicates that something is not performing appropriately in the coarse screen. So we'll want to check that on a fairly regular basis as a part of your maintenance checks and operation checks to look at the thickening factor of the screen, make sure that we're not fractionating pulp, making sure that the rotor is not worn out, the screen plate's not worn out, and we're getting excessive thickening across the screen itself. This is the heart and soul of any pressure screen, would be the screen basket. This screen basket is the partner to the rotor, and between these two components is what really performs the duty of the screen, which is to remove the debris that is large in two dimensions. That is the flake content that's removed or that comes to the screen from the pulp that is removed from the pulper, specifically in a continuous pulping loop, will have a fairly high flake content, for instance, for packaging grades. And coarse screens are required to be operated ahead of slotted screens or in fine screens because the coarse screens will remove the flakes much more effectively. Flakes have a hard time rolling up and fitting through the holes in the basket, whereas they can wedge themselves into slots and blind those plates over. So it's much better runnability with a whole basket in a coarse position. Now you'll notice that we have a corrugated surface on the feed side of this screen plate. The blow up there is of the inside of the basket because remember this is a centrifugal screen, meaning that the stock comes into the inside of the basket and moves outwards toward the outside. So this picture, this blow up, is of the inside or the feed side of the basket. And we have corrugations on the surface in order to provide micro turbulence, which gives us better consistency and better flow characteristics. Remember, we get more flow with a turbulent flow than we do with laminar flow. So we want to stir that surface up. And using these corrugations in the screen plate design is one way to do it. Another way would be to weld large bars on the inside of a screen basket, which also gives you macro turbulence. And this macro turbulence essentially accomplishes the same thing. That is, it stirs the pulp slurry up, gets more capacity through a given hole size, gives us better controllability at higher consistency, which gives us more capacity per screen area. All those are very good things. This is a secondary coarse screen. Uses a rotor and a bed plate type device, and you'll notice that around the periphery of the rotor are impact blocks These impact blocks are specifically designed to provide a close clearance and attrition for deflaking. So as the stock hits that screen plate and is swept out towards the periphery, then they will see the impact blocks, and any remaining flakes would be destroyed at that point. The circulation pattern inside this secondary coarse screen is such that the feed comes into the top, is set in a tangential motion here, and circulates around inside. The accepted pulp comes through the bed plate or the screen plate and is removed. And then the rotor generates a vortex, and this vortex creates a free vapor surface inside, which acts as a good collection point for lightweight removal. So for instance, in packaging grade where there might be some styrofoam contamination, this would be a good place to remove that styrofoam contamination. Then in the end of the pressure vessel here is flared out in order to promote this circulation that happens inside the rotor, inside the secondary screen here, and it has a heavy outlet discharge. It keeps the heavy material away from the rotor and gives you better, of course, longer rotor life, and provides another method for sand removal, staple removal, and heavy debris removal in the secondary coarse screen. Another option for a coarse screen is a centripetal screen. That is a screen design that allows the pulp to come from the outside of the basket to the inside. Rather than injecting the feedstock on the inside of the basket and asking all the pulp and all the debris to rub up against the inside of the basket, we now inject the pulp on the outside of the screen plate so that the heavy debris is thrown away from the screen plate, and it's only the pulp that then goes through the basket itself. Now the way that we accomplish that is that, if you can see in the graphic here, we've got a rotating basket. The basket is attached to the drive column here, and so it rotates, and there are stationary foils on the inside of the basket, that is on the accept side of the process, so that it keeps the screen plate clear. This means that the feed side of the screen is completely and totally open. That's a very good thing when you're dealing with stringy contaminants, when you're dealing with a lot of flakes, when you're dealing with styrofoam that comes in big pieces that you want to remove. So any lightweight contaminants are removed off the top of this centripetal screen, and the fibers are taken off through the center and down towards the accepts, or away from the accepts. Any heavy material, conversely, will come around and be removed in the heavy removal container zone there. This is the side nozzle off the side here. So the heavy material, like rocks or nuts or bolts, will come around and fall immediately out of the heavy junk trap at this point. The balance of the debris, the lights, and any rejects from the screen are then removed off the top and taken to the secondary stage. The heavy discharge is intermittent. The light rejects are continuous. In a flow sheet, the impact of using a centripetal screen might look like this, where you've got, in an old system using centrifugal screens, you'd have a high density cleaner and 2, maybe 3 stages of centrifugal screens. When you're using a centripetal screen, you can eliminate the high density cleaner and all its associated piping costs, pumping costs, and maintenance costs, and you can go directly to these centripetal screens, which then act as both the high density cleaner and the coarse screen together. Matching this technology with unique drum pulper technology has been found to be of an advantage, although many centripetal coarse screens are used in conjunction with low consistency continuous pulpers as well for the packaging grade processing of secondary fiber. Following a secondary coarse screen is often a separate tailing screen. In older mills, these might be vibrating screens, but in more updated versions is an atmospheric screen, such as this, where it uses a half of a screen plate laid down into a frame, into which a rotor is placed, and there is about a 1 millimeter gap between the rotor tip and the screen plate, so that as you turn the rotor, then it keeps the screen plate clean. and we add some dilution water typically in the body of the screen, which then washes the plastic debris away from the fibers. The fibers are recovered through the screen plate and taken off here with the orange indicated arrow, and then the plastics then report out towards the reject end and are removed from the screen on a continuous basis. So this is a totally enclosed screen that replaces a vibrating screen, does a much better job in terms of efficiency of removal, and of course it's a much easier screen to keep clean and to maintain housekeeping standards in a paper mill. This is an option for combining those two functions. That is, the secondary coarse screen and the tailing screen could be combined into one screen. And this is a deflaking tailing screen that takes advantage of the centripetal flow process again. The stock is injected here. The basket, in this case, rotates around. There's stationary foils on the inside, so the stock flows centripetally through the accepts and comes out in terms of the accepted stock and can be fed forward. Any heavy debris is dropped out immediately. This is kind of recovers from any mistakes that come through the system. And after all, this is a paper mill environment, so that is going to happen. And then the remaining material is going to be deflaked in this zone here. You can see that this is a photograph of the top of the rotating basket where there are actually deflaking bars welded to the top of the rotating basket. There is a stator plate which is then fixed inside the machine at this point, which allows it's the opposing force to the deflaking bars, so that we get that mechanical action and the shearing forces that we need in order to tear the fiber flakes apart. So once the fiber flakes are freed, then they are diluted and recovered in the upper screening zone and taken off and put back into the process. The balance of the material then progresses up the rotor and is delivered out the chute, which then ends up looking like this debris here, which is essentially a fiber-free mass of nothing but plastics, rejects, styrofoam, rubber, that sort of thing that ends up in almost every recycled fiber papermaking plant. So this is a good combination screen that allows us to do 2 or 3 functions in one unit and still economize on terms of floor space, capital cost, and operating cost. Moving on to fine screens. There are basically, fine screens are almost always centrifugal. There are centripetal flow designs out there, not used too much, but they do exist, where the basket is stationary, the foils are on the feed side, and the stock flows inward through the basket. But by far and away, the majority of majority of fine screens are centrifugal screens, as shown in this slide. There are 2 basic types. There's one that feeds from the top. That is, it comes in tangentially, feeds around inside the basket. The rotor clears the basket, and the accepts come through the screen plate and report out here. The rejects are retained on the screen plate and report out at the bottom. Conversely, there are designs which feed from the bottom. Basically a centrifugal screen turned upside down, so that the stock comes in at the bottom, rotates around, flows upward through the screen, and the rejects come off the top, with the accepts coming through the screen plate and coming off the side. There's no basic difference between the action of the 2 screens. It's just a design concept that helps to separate out the heavies in this particular case, and provides a vortex surface by which the lightweights can be removed effectively from the top of this screen. Both work extremely well, and both are used widely in commercial installations. All centrifugal screens use some sort of rotor. A rotor inside the screen plate will keep the screen plate clear. It will move the pulp from the feed end to the reject end, and of course it will achieve the desired effect of evening out the thickening factor and controlling the passing speed through the screen plate. Let's talk about each one of those things. The rotor will generate a pulse. There will be 2 components, basic components to that pulse. It'll be a positive and a negative. You don't want much of a positive pulse. The reason being that that will tend to push the deformable debris, i.e. stickies, through the screen plate. So if we can minimize a positive pulse, that's almost always a good thing. But you do need a fairly large negative pulse, and we want that pulse to bring accept stock, or water actually, back through the screen plate to remix, lower the consistency at the screen plate surface, and allow the fibers to then progress through the slots. And what happens with a screen plate most often is that it will, if it blinds over, it will start to blind over from the outside in because of the rotor phenomenon. That is, the rotor will come around, it will pull accept stock back through, and it's the water that comes back through. So stock will dewater on the accept side of the cylinder, and in order to provide dilution water for the inside of the basket. If it pulls too hard, if we have too much of a suction pulse, then it will tend to seal over, and the delta P through the screen plate won't push the accept stock back off of the screen plate, so it will not allow flow to go through, and thus the screen plate will plug. Now we have countermeasures for that, of course, that are programmed into the control system, but that's typically how the process would work. So we want to have a rotor design and a screen design that work in concert that minimize the plugging tendencies. So we design it with a large negative pulse. So then the stock on the screen plate surface is separated and mixed with fresh feedstock, which then lowers the effective screening consistency, allowing the fibers to move through the slotted plate. Now the design point that is easiest for us to get our hands around is something called a passing speed. And the passing speed is a purely mathematical calculation where we take the volume of stock in units of cubic meters per second, and we divide it by the total open area of the screen plate in square meters. The result is a meters per second passing speed. And that number indicates a relative term only. It's a theoretical term which says that it's so many cubic meters of stock going through an aperture, this slotted plate aperture, at a certain speed. And we understand that it's not a true representation of the actual speed. We have measured it. We understand that there are certain parts of the screen plate that are plugged at any given time, and so the average passing speed is really higher than what we calculate. But the real point that we can hang our hats on is that this meters per second factor is probably the easiest, most easily calculated, and most reliable term that we can use in order to quantify the capacity of a slotted screen system. Typical passing speeds, depending on the fiber type, might be anywhere from 1 to 2 or 1.5 to 2.5. It's completely dependent upon the consistency, the fiber type, the design of the system, but it's that handle that you can calculate yourself that really allows us to say, how are we getting all this capacity through this screen plate? We look at the meters per second, we look at the passing speed, and if it's way high, if it's 3-4 meters per second, then I'm not so sure that that's a good calculation or that's a good sizing. Whereas if it's too low, if it's 0.5 meter or 0.3 meters per second, then I can expect fractionation problems. So while it's not perfect, it's a pretty good measure. So rotors. We talked about screen plates and rotors having to work in combination with screen plates. And there are as many rotor types as you can think of. There are parabolics and drums and bump rotors and foil rotors and vaned rotors and dilution rotors. There are all kinds of rotors out there, and they're each designed for a specific purpose and a specific pulp type. But they all achieve basically 3 parameters. That is, transporting the pulp from the feed to the reject's end. They provide good mixing inside the screen. That is, we want to pull some of that water back from the accept side, remix it, and rescreen it. And we want to keep the screen plate clear. We don't want the screen to plug. It must first and foremost produce capacity. We have to have the capacity. And so we're looking for efficiency, of course, but we need to have runnability, and the rotor provides that runnability. So let's look at each one of these rotor types. The parabolic rotor, for instance, the one here on the far left. The parabolic rotor is designed such that as we accept, this is the feed end of the rotor, so as we pull stock in and we start to take off the water and the short fibers off the top end of the screen cylinder, then the volume decreases inside the screen cylinder. And so as a result, we've made this parabolic shaped rotor that also reduces the volume. and that keeps the axial velocity the same from the top to the bottom. So when we're building a screen plate with a high L over D ratio, it's got a longer length to diameter ratio, then we'll want to use a rotor that also controls the interior volume of the stock so that we don't dewater, get an excessively high thickening factor. The drum rotor, on the other hand, and one next to it, the drum rotor is used so in screens where they don't have such a high L over D ratio. It might be 1 or less, for instance. And this drum rotor is designed to even out the stock flow from the top to the bottom of the screen so that we don't have excessive thickening factors. We have about the same passing speed from the top to the bottom in the axial direction so that we have about the same screening action all throughout the entire circumference of the entire screen plate. So the drum rotor is a very, very useful screen for situations where you have stickies removal concerns, obviously in secondary fiber plants in particular. The bump rotor is a fluidizing rotor, which we use in fractionation screens where we're not really trying to separate debris as much as we are trying to separate fiber types by length. So we'll fluidize the pulp using a bump rotor. Also used in whitewater filters and in black liquor filters, we'll use this bump rotor as a fluidizing type rotor. And there are many, many, many types of foil rotors which are used to increase the residence time of the pulp inside the screen plate, which then allows the stock to present itself a number of times at the screen plate to be separated. So foils still produce the same effect, that is to lift the stock off the surface of the screen plate and to pull some of that accept stock water back in to redilute and to rescreen to make the maximum use of the effective screen area inside the pressure screen. So how do we choose the right screen cylinder? This is an extremely complex technology, one that is not completely modeled well, and so we can't really tell for every instance about exactly which screen plate it is. We can come pretty close, and these are some of the parameters that we look at. Certainly not all, but I would say these are the big three: the contour height, the slot width, and the pitch. The contour height is the depth of the profile. That is, if we look at the feed surface of the screen cylinder, we'll look at the depth of that profile. How big is the drop from the surface of one slot down to the surface of the other slot? Typically, the lower the screen contour, the higher the separation efficiency, but also the lower the possible feed consistency and the lower the capacity. So if I've got an existing screening system, it has a fairly low profile depth to the screen cylinder, I can get more capacity, I can get better consistency, higher consistency operation at the same passing speed if I just improve my contour depth. Next would be slot width. Once I've picked my contour depth, then I look at slot width, and as you would expect, smaller is better. That if I can go with a smaller slot, then I'll get better debris removal, better stickies removal. That's not 100% the case, obviously. There are certain instances where that might not be, and that would be when I've got a smaller slot and a deeper contour. These two factors play off of one another, and so it's not always a clear-cut decision. So you can't always say that it's smaller is better, but in general, I think slot width is the overriding factor after contour height in terms of determining screening efficiency for slotted screens. And then lastly would be pitch. That is, how close can we put the slots together? The closer the slots are together, the higher the open area and the lower the resulting passing speed for a given capacity. And this is a very good thing. So if we can increase the open area by giving a smaller pitch, or that is a narrower pitch to the wires or a narrower pitch to the slots and how closely we can put them, then we can increase the open area, increase the capacity, and without sacrificing the efficiency. The problem is that if we get them too close together, then we have hydraulic interference between one slot and the next and the following slots, and we actually lose capacity by having more slots per inch. So you have to play with this parameter as well, along with the profile depth, along with the slot width and the pitch, in order to get a screen that performs suitably in your installation. So that's why I put at the bottom that you really need to consult a screen supplier when you have questions, not if. But involve the supplier, involve a number of suppliers, and they will help analyze the system, make recommendations, and then of course recommend a solution, which then is for trial, which is the proof is in the pudding. Put it in the mill, try it out, and you can see the results. So let's take a look at the different cylinders that might be recommended. There are milled cylinders, and these cylinders are made by starting with a flat piece of sheet steel and sawing a contour in one side, flipping it over, sawing the slot width in the other side, and then rolling it up, putting flanges on it, putting rings on it, and putting it in the pressure screen. This is a very, very good, robust screen cylinder design. It happens to be fairly low open area, so we have to be a little bit concerned about the situation, the process considerations, but it's extremely robust, very rugged, very reliable, and was the basis by which all the slotted screening technology came into use today. Still a very good, reliable technology. There are wedge wire cylinders, and these cylinders started out life is resistance welded baskets. We still make these today. It's still a usable technology, but it's a fragile technology. The method of manufacturing is such that the wires are resistance bonded to the supporting wires as they're wound around a mandrel. Then they're cut off of the mandrel, flattened and re-rolled in an opposite direction. All those stresses are put on the basket, and all that stress ends up as a residual stress in the structure itself, so that under load these can be subject to failure. But a very, very good method by which we can get a higher open area for the same circumference and length of a screen basket. So by using wedge wire, we were able to get essentially 100% open area in terms of its slot width from the top to the bottom flange. That was a huge leap forward. In spite of its fragility, it really added tremendous dimensions to what we could do with slotted pressure screens because of the increased open area, the increased capacity, the lower the passing speed, the improved performance, the narrower the slot width. So we really made a huge step forward when we started using wedge wire technology in slotted pressure screens. In order to overcome the fragility issue, we went with mechanically clamped. And now I apologize for the illustration here, but what I really wanted to illustrate, I couldn't find a good picture, but what I really wanted to illustrate was that the wires in this mechanically clamped version have a small bulb that are extruded into the end of the wire so that they are held mechanically. When we roll the basket together and seam it, there is no welding that's required. And by eliminating that resistance weld, we've certainly eliminated the point for failure and increased reliability tremendously. So this is still a rolled basket, and we still have good control over the profile, that is the extruded shape of the wire. We have good control over the slot width dimensions, but because it is rolled, it does have some residual stresses, and it has some deformities that are part of the mechanical manufacturing process. Lots of different profiles are available, lots of different slot widths are available, so lots more flexibility, much more rugged, and a pretty good solution. Lastly, we have a TIG welded basket. Now this is also a wedge wire basket. That gives it all the same flexibility. That is, we can extrude these wires in any shape that we desire. In this particular case, you see that they have a very deep draft that's set into the support wire. The point here is that it gives it a lot of rigidity. That is, it gives it a lot of resistance to bending moment that's applied by the rotor as the stock moves across the surface of the screen plate. The trick to this basket is that it's made seamlessly. It is not rolled. The support rings are cut out by a laser, and all the dental work is cut into it, and then it is assembled in a comb arrangement. The wires are hand fit into each slot, and then the flanges are put on and it's tilted over and TIG welded on both sides of the support rings. This gives this basket an extremely good amount of structural strength, and it gives it a very, very narrow slot width distribution, standard deviation, a very narrow distribution. So we have a good repeatable slot width every single time. A very good rugged basket is simply an advancement in manufacturing technology, which really allows this basket now to be used under high consistency situations as well as low consistency. It allows it to be used very reliably in head box applications. Really, it's increased the ability of wedge wire slotted baskets to be used throughout the mill, throughout the recycle plant. And here's a small graphic of the flow that would be expected through a slotted basket. You can see this is the 100% open area. The slot width is opposing each individual wire. And you can see that I can make this wire shape almost anything that I want. I can tilt it any direction that I want. So as a result, I can get any profile depth, any pitch, and any contour shape that I want, and of course any slot width that I want. So it gives me all 3 degrees of freedom that I'm looking for in designing a screen plate. And when we talk about contour, this is an illustration of exactly what we're talking about. This slide does a couple of things. It talks about the contour depth, and you can see here where the red color is an indication of the velocity of the flow, or how turbulent the flow is. With a low profile height, and I'm talking about this distance here, the distance between the bottom of the groove and the top of the screen plate. This is the feed side of the screen plate out here. That distance, if it's low, then these eddy currents in here are fairly low, and the velocity through that slot is going to be fairly low for a given slot width, a fixed slot width, and a low profile height. On the other hand, as I increase the profile height, this depth is deeper than this depth, and this depth is yet deeper still than this depth. You can see that the turbulence increases as the depth increases. That gives me all the benefits of having a higher profile. That is, I can operate at higher consistency because I get more turbulence. I can operate with a smaller slot and still have the same capacity, but it also gives me a reduction in fractionation at the same time. The difficulty is that I can't overcome the loss in efficiency by making a slot width that is small without being very cautious about pitch and about profile depth. So for a screening system design, usually there are 3 or 4 stages required depending on the capacity. The primary stage is for efficiency. The secondary, tertiary, and sometimes quaternary stages are for fiber recovery. A lot of times the secondary can be fed forward so that it can add to the capacity and reduce the overall size of the screening system. Makes it much more economically advantageous. The feed consistency for slotted screening systems in recycle plants varies, depends on the fiber type and the design and the rotor. Typically you're looking at it at 1 to 2%. There are lots of systems out there that are running 3.5%. They have a little different focus on them, but there are some systems, consistency should be in that range when you expect to look at them. In comparing screening systems and screen system design, consistency is an important consideration for looking at how we achieve efficiency. Solids losses. You won't buy a slotted screening system now without a fiber loss guarantee. So solids losses from slotted screening plants typically have ranged into 1 to 1.5%. We're finding new ways with new tailing screens to keep that fiber in the system, which gives immediate payback because of the high cost of fiber. Passing speeds. Passing speeds will range, again, usually from the 1 to 1.5, maybe 2 meters per second. More recently, the systems are being designed to go up to 2.5 meters per second, depending again on the consistency and the rotor type. The ink stocks, you can expect to find smaller slots, 4 to 8 thousandths of an inch, or 0.1 to 0.2 millimeters. Packaging grades, however, will use larger slots simply because the fiber is bigger, tougher, a lot more softwood, is not as thoroughly pulped, it's not as flexible, and so we'll use larger slots in packaging grades. Thickening factor, we talked about thickening factor earlier. The thickening factor is typically going to be in that 1.5 to 2.5 range. If it gets up to 4, 4.5, that's typically a tailing screen stage, and you're going to want to add some dilution water, do something with it, but track it. When you do your measurement of your screening plants, look at thickening factor, keep a database. If the thickening factor goes high for some reason, that's an indicator that you need to investigate why. Something's worn out, something needs to be replaced, some maintenance needs to be done. So let's look at screening system checks. What do we do to check a screening plant that's existing? We'll sample from the feed and accept streams of each stage in order to test for dirt count, consistency, the stickies, and the freeness. We'll want to look at the final stage rejects to see what the system is ultimately throwing away. We'll note the flows and the motor loads during sampling. That's very, very important when you're doing an analysis of the system. We'll construct a mass balance, very simple with the tools that we have available to us today, to use an Excel spreadsheet, for instance, to simply enter in this data and do the calculations automatically so that we can see what our flow splits are, see what our reject rates are by mass and by volume, calculate our thickening factors, look at the loading in terms of how many tons per day per square meter are we putting through, what's our passing speed, how many cubic meters per second per square meter are we putting in. Okay? We're going to want to look for excess fractionation. That is, we look for excessive thickening factor or a big drop in freeness. That'll indicate that something needs to be done in terms of maintenance. Maybe a different screen cylinder type is required, maybe a different rotor change, maybe a rotor speed change. All these things can be indicated by looking at the freeness drop. And then ultimately you'll want to report your system efficiency for dirt and stickies removal, the two things that slotted screening plants are installed to do. It's the #1 option for removing stickies in a recycled fiber plant is to do slotted screening. So in summary, coarse screening usually done with holes. The coarse screens remove the flat debris and concentrate flakes for further treatment. It can be done efficiently with many different combinations of rotors, baskets, and flow concepts, that is either centrifugal or centripetal. Fine screens are usually done with slots. They remove small cubical debris, typically classified as stickies. It can be done efficiently with many types of rotors and baskets, but the centrifugal flow pattern is usually the prevalent one. Thank you for your attention.